How's everyone doing today? Good to hear. Any questions, needs, concerns, etc. before we get started today? Alright. Well, past couple days we've been looking at rotational motion, looking at the ways that we describe rotational motion, and also talking about centripetal force and how it can cause rotational motion. In talking Monday about centripetal force and how it causes objects that normally want to move in a straight line, forces those objects to begin moving in a circle around something, I want to again bring up, before we review any of that old previous information today, that linear motion and rotational motion can happen at the same time. Centripetal force stuff from the other day is meant to kind of act as proof of that. So there's multiple ways that linear motion and rotational motion can overlap, that they can occur simultaneously. And so sometimes it's useful to consider how one form can be turned into the other, how the two directly relate to each other. We've got the very similar formulas between linear motion and rotational motion. All the logic between displacement, velocity, and acceleration is still intact. But in the cases where both are happening simultaneously, the two worlds don't have any immediate effect on each other as per just these formulas. Because right now all the linear formulas only have linear stuff, and all the angular formulas only have angular stuff. Centripetal force and the formula for centripetal acceleration is kind of the first thing we did where a formula kind of involved both at once. I want to point out that there are a couple of formulas that exist specifically to translate rotational motion and linear motion back and forth between each other. What these formulas would do for us are, for example, say we have a bike tire, and as this tire rolls forward, it would displace both angularly and linearly at the same time. It is both spinning forwards, but also moving meters forward simultaneously. That delta x and that delta theta are connected because the more times the wheel rotates, the further forward it rolls, correct? So the two worlds are related, and these formulas here in the middle, which are also between the angular and linear boxes on your formula sheet, they live right here. These exist to demonstrate how the two worlds are connected. How, for example, how something rolling forwards, how many times it rotates, is tied directly to how far forwards it moves. And suddenly realizing that I didn't rewrite my notes. Forgive me for a sec. It says S up there because S stands for arc length, but I meant to change it to delta x to match your formula sheet, so apologies. So all those formulas in the middle are designed to tell you how something's linear motion translates directly to its linear motion. Again, if something is rotating forwards, there's a good chance that it might be rolling a distance forwards at the same time. The variable that will allow you to convert one into the other is basically just the radius of the tire. A bigger tire will actually roll further forwards per number of rotations than a smaller tire. I usually have a smaller wheel up here. Oh, this will do. To kind of demonstrate this, that the size of a wheel affects the translation of rotational linear, I am now going to roll two objects of vastly different radius. First is the bike tire, second is this golf ball. And conveniently, it does have a line on the side so that you can see the full 360 degrees. So first, wheel, we are going to see how far this thing moves forwards with a full rotation. That would be 360 degrees, 2 pi radians. So from start to finish, it would roll to right about here, over the edge of the taller part of the desk. Now, the golf ball. I'm going to start at the same place. Note, the black line is on the top. And we're going to rotate it a full 360 degrees, and it's done. For each of those motions, both objects have the same angular displacement. They rotated through the same number of radians, but because they have different radii, they roll a different distance forwards. So whenever translating linear to angular, the radius of the rotation affects how one translates into the other. And the same is true for angular velocity and angular acceleration as well. So if you ever have an object that is rolling forwards or even angularly accelerating, the radius of rotation, the radius of the centripetal acceleration, or even just the radius of the rolling wheel will allow you to turn any angular information into linear information and vice versa. So that's what those middle formulas are, and we're going to try to summarize all of those rotational things we've talked about together in some more examples today. Questions so far? Okay. Bless you. First, let's start out with just utilizing these formulas, and then we'll tie centripetal force and centripetal acceleration back into it. Let's just look at the wheels of a car. Not that dissimilar from that bike wheel over there. A car is going to be traveling at 29 meters per second directly forwards, so that is the forward linear velocity of the car, but also as a result, all of the wheels that are attached to the car. So velocity initial linear is 29 meters per second. The car is now going to begin slowing down at an angular acceleration of negative 1.75 meters per second squared. And we have been told that the tires of this vehicle have a radius of 0.33 meters. That is specifically their radius, not their diameter. So from middle to edge, 0.33 meters. And that's the information we want. We want radius. So, first question. How many radians does each tire rotate through before the car comes to a complete stop? We've been given linear velocity initial, linear acceleration, radius, and we would like to know delta theta. the beginning of the course, looking at those first 4 formulas that we ever talked about, we know that if something's accelerating, it's going to be displacing while that happens, correct? That's what formula 3 and 4 tell us. So as the car slows down, it's still moving forward while that happens, so there will be some delta x forwards while hitting the brakes. However, delta x is not specifically what we've been asked for. We want rotational displacement, because if the car is moving forward, its wheels are also spinning while that happens. So rather than just delta x, we want delta theta. So thoughts on how to get there from the information we have? Yes, we can. So I'm going to tab backwards real quick and look at the formulas. Formula 3, for both linear and rotational, talks about how, while you're accelerating, you are displacing forwards. So, linearly, vehicle is slowing down, it's going to move some distance forward as that happens. Likewise, the wheels should also be angularly decelerating at the same time, and as a result, the wheels will still rotate some number of times before coming to a complete stop. The issue is, we know V initial and A and want delta theta. Well, okay. We actually don't know time, so instead of 3, I'm actually going to point at 4 instead. We know V initial, we technically know V final, because we're looking at when it stops. And we know A, but we want delta theta. Now the thing that I'd like you to pick up here is, we have all the information we need to find delta x. We can figure out the distance the car slides forward as it stops, and we can turn delta x into delta theta since we know the radius of the tires. The two worlds, rotational and linear, are connected. So as long as you know the radius of the wheel, you can turn one straight into the other. So if we find delta x, we can turn it into delta theta. Alternatively, we could also turn these into their angular counterparts and just work the rotational version of the formula. Either option works. But, backing up to demonstrate my point. We know V initial, we technically know V final, because again, the car is going to stop, so that would make VF 0. We know A, if we find delta x, we can turn it into delta theta. So, final speed is 0, initial speed was 29, 2 times the negative acceleration, and then delta x. So, how far forwards does the car roll while it slows down? Come again?
29.
29 meters per second is the initial speed.
What was the question?
What's delta x?
Oh. 240.3.
Yes, very good. So that's the distance we roll forwards while we are hitting the brake before we come to a complete stop. That's again linear displacement. And we can convert that into angular displacement. First though, any issues or differences finding this number? Okay, so now we've got delta x, we want delta theta, we also happen to know radius of the tires. So I would recommend we use this translation formula in the middle to just turn the linear thing into its angular counterpart. Delta x equals r times delta theta. Delta x was 240.3, r is 0.33 meters. Solve for delta theta. You're actually going to get an even bigger number. You'll get about 728.2. What would the units for delta theta be? I think I saw a few people mouth it. Radians, which I tend to just shorten to rad. So this does tell us how much the wheel spins, how many times the wheel spins. It's just in the unit of radians. And the reason that we got radians out is because we took the linear displacement, we divided it by meters. That kind of cancels the meters out, and that just leaves us with the kind of inherent unit that relates radius to the circumference of the wheel, radians.
I'm so confused why we couldn't use the last equation on the right side.
This one?
Like,
We absolutely could.
oh,
We would
okay.
just need to turn V into omega and A into alpha first. That would absolutely work.
How would you turn V into? Okay.
So one way or the other, we have to turn something linear into angular. You can either do all the linear stuff first and turn the answer into angular, or you can take your starting variables, make them angular, and then use the angular version. Both work totally fine. They get you the same place. Now, radians are still kind of a weird unit for rotation. So to kind of help build up the frame of reference for this, I'm going to quickly convert this into degrees and rotations, just to show more practically how many times the wheel would spin. 2 pi radians equals 360 degrees. Therefore, we can convert radians into degrees. I'm just doing this quickly to demonstrate the frame of reference. The wheel would rotate through over 41,000 degrees while it is slowing down, which even still might be kind of weird to talk about. Usually you only hear like 360 or 720 degrees. We don't usually go above that. So instead, I will also convert this into number of rotations. Because if 2 pi radians is 360 degrees, that means 2 pi radians is also equal to a single full rotation of the tire. So similar conversion factor can tell us that the wheel spins about 116 times. Yes.
Are we gonna need to do that math on this?
Yes. Now, again, I would never hide conversion factors from you. These are the two that I used here. And get this out of the way. Suboptimal, pardon me. All I did here was I converted radians into the two other units for rotation. First was degrees, noting that 2 pi radians is equal to 360 degrees. Also, since those both equal 1 full rotation, 2 pi radians equals 1 rotation, and this would convert it into number of rotations, which is just literally how many single times did the wheel spin as it slowed down. So I would say these were the conversions. You can write this on your formula sheet. I would not hide this from you on a test. I treat these as just normal conversions. All this to say, the wheel spins a lot. It spins several times as this happens. So this answer we got is many, many rotations. We do need to keep it into units of radians because all of those formulas up here are designed to take radians for all of those rotational units. But it's okay to convert it into rotations if that helps your frame of reference. Sometimes they might tell you number of rotations and you'd have to turn it back into radians, or vice versa. Questions so far? All right. Next question. What is the angular speed of the wheels when the car has traveled half of that total distance? Basically, at what speed will everything be moving when the car has halfway driven to its finish point? So when the wheels have spun half of this, or when the car has moved half this distance forwards.
So would we still use that same equation and just plug in a different R?
Not a different R, because
Like
the tires are the same size.
Oh, sorry.
Note here that the thing we're after here is omega final. They want to know the final angular speed of the tires as they slow down. The final angular speed at this point in the mill. We used Formula 4 earlier, and I'm going to keep pointing at it because I think it's a good idea to use it here. Since we don't know time for any of this, all the others have time in it, but we don't know time, so Formula 4 is nice for that reason. Linearly, we know the rate of deceleration of the wheels, we know starting linear speed, we know the linear position that the car would be at. It would be half of that total delta x we found earlier, but all of that would tell us the linear speed at that point. Alternatively, in this formula, we want final angular speed for that moment in time. We know we can find how many times the tires would spin by that point. The problem is that we don't have the angular version of initial speed or angular deceleration. So both formulas will tell us what we want, but we still have to convert something back and forth from linear to angular. We can use this formula, find linear VF, convert that into angular VF, or alternatively, in this formula, the angular version, we would have to convert V initial and acceleration into their angular counterparts first before we could use it. So which one you do is kind of up to you.
Can you do the one like where you convert and then just so we can like see what it looks like?
Absolutely. So once again, just to put the question back up, what is the angular speed of the wheels when the car has traveled half of the distance to slow down? So as you asked, I'll put up the angular version of the formula. So what we're after again, we want to know the speed the wheels are at after decelerating for half of the distance. Not the totals, not the total to slow down that we found earlier, but half of it. So delta theta, we would end up putting in this number divided by 2, the point where it has moved half as far forwards or spun half as many times. Omega F is the thing that we're after, and that means we need to figure out what to put in for omega I and alpha. Those are the angular counterparts of initial velocity and acceleration. So we can take the initial velocity, the linear initial velocity and linear acceleration, and convert them into omega initial and alpha. Once again, those conversion formulas, I'm running out of space, I'm going to do them over here. Those conversion formulas in the middle part of the equation sheet. Basically, if you have the angular version, you multiply it by radius to get the linear version. Alternatively, if you have the linear version, you'd want to divide it by radius to get the angular version. So, if our linear initial speed is 29, 29 equals 0.33 times the angular counterpart to that initial velocity. Meanwhile, if our linear acceleration was a negative 1.75, that would be equal to radius times angular acceleration. So we can figure out omega I and alpha to put into our other formula. Anyone's math disagree with mine? All right, so this is the angular version of our initial velocity. This is radians per second, how fast the tires were rotating before we hit the brakes. This is the angular deceleration once we hit the brakes. So this represents the change in the tire's rotation every second. Just just took the linear stuff and turned it into its angular counterpart, and with that done, we can now use that in the angular formula. Omega f is again what we're trying to find, so we'll leave that blank for now. Then is omega initial squared plus 2 times alpha. And then for delta theta, we're plugging in half the number of radians since we're trying to find the speed at the halfway point. Does anyone disagree with about 62? Since this is angular speed, the final unit would be radians per second. This again tells you how much the wheel is rotating at that point. Even though we've traveled half the distance, the wheel has not actually reduced itself to half of its initial speed. Deceleration's kind of weird like that. Questions so far? Okay. Lastly, just kind of as more conversion practice, I'd like you guys to take this number, 62.14 rad per second, and turn it into the unit rotations per minute, since that's the unit that your car tends to tell you. So we got 62.14 approximately radians per second. How would one go about turning that into the similar unit of rotations per minute? If you've ever paid attention to your RPM meter, and frankly I don't usually, you notice that the numbers tend to be pretty big. So if you did the conversion correctly, you get a similarly fairly large number. If you're starting in radians per second, you need to cancel out radians and replace it with rotations. The relationship there is again 2 pi radians is 1 full rotation, since 2 pi radians is equal to 360 degrees. Rotations is a unit. And I would divide by that to cancel out rads and replace it with rots. Then turn seconds into minutes, You want to multiply by 60 seconds to cancel out the seconds on the bottom and replace it with minutes, and you should get about 600. Yes?
I got about like 6,000.
6,000. Did I mess up? Hmm. 62.14 divided by 2 divided by pi times 60. Yeah, I'm still getting about 600.
If you just type in 2 pi, it's different than 2.
So that's your calculator messing up on order of operations. Because if you just type this into your calculator seen as like this, if that's what you put in your calculator, again, calculator's kind of dumb. It's gonna divide by 2 and then multiply the answer by pi, which would actually end up making your answer about 10 times bigger than it's supposed to. So I would put parentheses enclosing the 2 pi.
So the 62 is in seconds, so we're trying to go to minutes, right?
Yes. Since seconds is on the bottom, the way that I do it, I would multiply by 60 seconds to cancel out this seconds in the denominator and replace it with minutes instead.
Okay. I thought the one had to be on top.
Not always.
Okay.
The rule that I would say to give and follow is to make sure the units cancel out correctly and end up in the right position. That's more important than wherever a 1 needs to go. The 1 does usually end up on top if we're doing like hours or minutes to seconds, but this is literally the reverse. We're going from seconds back to minutes, so that's why it's opposite.
Okay.
How you guys feel? I will go ahead and say, rotation's weird. It's just inherently weird. Humans don't tend to think in terms of spin. We tend to think in straight lines. And that's fine. It makes this section just odd. And that's, if this is weird, if this is taking you a minute to wrap your head around, totally fine. That's why we're spending 2 weeks on it. It's part of the course. Any specific questions in your brain at this moment? Okay. Now, I want to do just one last quick example, because we didn't practice centripetal acceleration yet today. So, small last example. My intent is to kind of give this one to you guys and see what you can do within the next couple minutes. This is again, this one, so we're switching gears, last thing we're doing today. This is going to be a centripetal acceleration question, so the stuff we talked about on Monday. Here we're going to have a fighter jet moving very fast, and it's going to start turning very fast. If you've ever heard about pilots blacking out if they turn too quick, if they undergo too many G's, that's the sort of thing this is about. Whenever a jet is moving in a straight line, everything tends to be in equilibrium, but for the jet to turn, it has to physically rotate its body and change all the direction that the forces are acting on it. And so for the jet to turn, it has to physically rotate, change the angle of the applied forces, Like literally it's rotating its wings to change the direction everything's pointing. And create some centripetal force inward in order to start turning. So there's technically an invisible circle that it is banking around here, and therefore it has some turning radius. If you've heard the term turning radius before, this is what it's referring to. It's the physical distance from your vehicle to the center of the imaginary circle you are turning around. And in jets, turning radiuses tend to be very big because they are moving very fast. This particular jet has a mass of 2,000 kilograms. It is flying at Mach 2, which means twice the speed of sound. This is the speed of Mach 2 in meters per second, 686. When it turns, it needs to generate centripetal force, and the pilot has to be aware of how much centripetal force they can withstand without becoming unconscious. So, if said fighter pilot is able to withstand a centripetal force of 17,000 newtons, what would the jet's turning radius be? And we'll put all the centripetal formulas from the other day back up on the board. Centripetal force equals mass times centripetal acceleration. Centripetal acceleration is velocity squared over turning radius. So, give you guys a couple minutes to figure out what the turning radius of this jet is. Answers yet?
I did it differently,
Okay.
but I got 55,364.
Yep. So if you think your vehicle is a bad turning radius, jets are worse. They do not turn anywhere near on a dime. This especially if they're going very fast. This example may not totally match reality because there's factors outside of just these numbers that affect the way the jets move. A lot of it has to do with air resistance. But overall point is, jets take a very large distance to turn if they're moving quickly. Actually, the same is true of any fast-moving object. How you guys feel? All right, Friday we're going to keep talking about rotation and centripetal force. We're going to bring the moon back into things and talk about specifically how gravity can act as a centripetal force. And let me know if you have any questions or need anything. Until then, have a great day. Centripetal force. I have a machine that spins things very fast.